Hi everyone, welcome back. In this video, we are going to cover another problem on power optimization of a given digital circuit. So guys, if you have not subscribed this channel so far, I would request you to please do subscribe this channel and press the bell icon so that you would get notified as soon as I upload a new video. Now let's focus on this problem. So guys, the objective of this problem is optimizing the given circuit for minimum power consumption. So guys, first let's understand the functionality of this circuit. If you see here, we have a multiplier hardware, then a adder hardware, then we have a multiplexer, and there is a flip-flop. So if we carefully analyze this circuit, whenever the enable signal is 0, the output of multiplier and adder circuit is used by the downstream logic. Let's consider this as a downstream logic where the flip-flop is basically consuming the output of multiplier and adder through the max selection. So whenever the enable is low, the output of multiplier and adder is basically used by the flip-flop. But whenever the enable signal is high, the flip-flop output is basically going back to the flip-flop input, or the output of multiplier and adder is not used when enable signal is high. That means whenever the enable signal is high, because of the toggling of the input signals, the multiplier and adder will have some switching or some processing to calculate the result, which is even not used by the downstream logic. So if somehow we can make sure that whenever the enable signal is high, there is no switching activity happening by the multiplier and adder hardware. And if I make it more simple, whenever the output of multiplier and adder is not used, if somehow we can make sure that the input to the multiplier and the adder are static. So if the input at multiplier and adder are static, that means there is no switching activity happening inside the multiplier and adder hardware circuit. So guys, in simple words, we have to make sure that whenever the multiplier and adder hardware output result is not used, the input to the multiplier and hardware should be static and there should not be any toggling. So guys, you can pause this video here for some time and you can think of any kind of solution which will help us to make sure that the input signals to the multiplier and adder are static whenever the output of multiplier and adder is not used by the downstream logic. And I will be explaining the solutions in further slides. So guys, now let's see the solution. So if we modify the circuit as shown here, so basically we have put a latch, negative level sensitive latch for the three inputs which are A, B and C. You can assume like three latches placed for each of the inputs A, B and C. Or if this latch is a 3-input latch, we can use one latch itself. But basically the idea is latching the input A, B and C. So if we use a negative level sensitive latch here, now let's see how the functionality of this circuit is going to be different. So whenever the enable signal is high, the output of this flip-flop is basically going back to its input. But whenever the enable signal is low, the output of adder will be going to the flip-flop input data line. That means whenever the enable signal is low, the output generated by the multiplier and adder circuit is going to be used. Otherwise, the output which is generated by the multiplier and adder circuit is not going to be used. So now let's concentrate when the enable signal is high and the output of multiplier and adder is not going to be used by the downstream logic. How the switching activity is getting minimized. So whenever enable signal is high, this is a negative level sensitive latch. That means the data at the input of the latch are basically going to be in latching state. That means if the data when the enable signal goes high was 0, 0, 0, that means during the time the enable signal is high, the latch is basically latching this data. So the latch output is 0, 0, 0. And it is basically static at the inputs of multiplier and adder circuits. So during the time enable signal is high, The data at the input of the multiplier and adder are static, and hence there is no switching activity happening inside the multiplier and adder hardware, and hence there is definitely going to be dynamic or switching power reduction. And whenever the enable signal is low, that means this latch is a transparent in that particular scenario, and whatever the input data is present at the input of the latch, it is going to be same at the output and same data at the input of the multiplier and adder hardware circuit. So guys, this is one of the solution to reduce the dynamic power consumption for these kind of hardware circuits. So here is the summary of whatever we have discussed so far. Whenever the data path result is not being used, that means whenever the output of the adder is not used, the data can be kept quiet by isolating it from its input with a latch. So basically we are isolating the input data whenever the result of the adder is not used. So the power savings are due to the lowered activity in the data path operator. Now let's see what are the trade-off of this solution. So of course there is an extra latch circuit we have to keep in the data path that will definitely going to increase the area of the design, and because of the added latch in the data path, we have to carefully handle the timing of this path as well. So these are the trade-offs associated with this particular solution. I hope each and every point of this problem statement is clear. If you have any doubts, please write down in the comment section. Also, if you like this video, please hit the like button and do not forget to subscribe this channel and press the bell icon so that you would get notified as soon as I upload a new video. Thank you very much.